So in this module, we're going to use the formalism of general measurements that we just introduced in order to define an important operation on quantum states, which is called the partial trace. So what's the goal of the partial trace? Well, imagine that you're given a description of a quantum state that's defined on two systems, A and B. And this quantum state is specified by a density matrix ρAB. Now suppose that you don't really care about system B, you want to ignore it. Technically, we'll say that you want to trace out system B. What you'd like is to have a description of the density matrix of the system that is associated with A only. So this is called the reduced density ρA associated to the state ρAB on system A. So this is our goal. How do we perform this operation? So let's look at a couple simple examples to get started. The first example would be a density matrix that's given like this. So it's a uniform mixture with probability half both systems A and B are in the 0 state, and with probability half both systems A and B are in the 1 state. In that case, it's pretty intuitive what we'd want to say the reduced density of the system is on A. A natural guess would be that this reduced density should again be a uniform mixture of, in the first case, the A system is a 0, so I want to put a 0 here, and in the second case, A is in a 1, so I want to put a 1 here. And it turns out that this is the correct answer. This indeed represents the state of system A. But here, this example was kind of easy in the sense that this state is a mixture of product states. And when I have a product state, it's natural to say that, well, if this is a product state, the B system is in a certain state where I don't care, I'm tracing out the B system, getting rid of this, and then I get what I wrote down for the A system. But let's look at a more complicated example, the kind of examples that will arise when we consider cryptographic applications. So suppose the state is a tripartite state, A, B, and E, where A could be a user, Alice, B could be another user, Bob, and E would represent the system of the eavesdropper, Eve. And let's imagine that my state is like this. It's a uniform mixture, again, with probability half A, B, and E are in the 0 state. This is a tensor product state, pretty straightforward. But then with probability half, A is in the 1 state, and B and E are entangled. They're initialized into an EPR pair. In that case, I can again ask the question, what is the reduced density of this state on the A system or the B or the E system? Let's look, for instance, at the B system. As before, I'd like to say that with probability half, the B system is just in the 0, so that's okay. And then with probability half, well, I have something more complicated. This B system is entangled with E. Can I really talk about it on its own? It seems like I need to take E into account. But that's not good. In practice, maybe E is very far away. I do want to be able to describe the state of B system completely ignoring E. It's not going to be a pure state, it's going to be a mixed state, but I ought to be able to find a description of that state. So how do we do this? And so the trick to compute this partial trace is going to be to perform a measurement on the B system. The idea is that I'm only interested in describing the A system. So this description, whatever it is, should be independent of any local operation that's performed on the system B, including a measurement, as long as the outcome of this measurement is kept local to the system B. The advantage is that we're going to use this measurement in order to find a convenient description of the state from which it will be clear what the reduced density on A should be. So let's do this. Let's choose a measurement on system B. So what we want is to do a partial measurement. We've seen how to do this. We can use the formalism of POVMs and introduce the following POVM elements. MB, which is the identity on A, tensored with the rank 1 projection on basis vector B for the B system. And this is a projective measurement, so we can use as cross operators EB the same as the MB. So we do have that EB squared is equal to MB as is required. Now we can see how the state evolves under that measurement. We know that if we perform the measurement, the probability of the outcome B will be given by the trace of MB applied to ρ, and the state will evolve into a post-measurement state Rho B, which is equal to EB Rho EB dagger divided by the probability of B, which I can rewrite using the form of EB in the following way. I can write it as a state that takes the following form. So it's made of two parts. The first part is only on system A, and that's the post-measurement state on A only, conditioned on having obtained the measurement outcome B for the B system. What's important about this state is that it's a tensor product state. And of course it's a tensor product state because I performed a complete measurement in the basis of the system B, so I know that B is projected to a pure state, the pure basis state associated to the measurement outcome that I obtained. So that's what's going on here. And the A system itself is projected to some post-measurement state, which doesn't need to be pure. In general, it's going to be given by a density matrix on the A system. That's the density matrix of the A system, conditioned on having obtained outcome B on B. So now if we don't do this conditioning, if we just look at the average state that's obtained, averaging over all possible outcomes on B, then by performing this measurement, what we've done is that we've evolved the global state Rho AB into a state I could call Rho tilde AB, which is the sum over all measurement outcomes of the probability of obtaining that measurement outcome times the corresponding post-measurement state. And we can write this explicitly. The probabilities will cancel out. I forgot to divide by probability of B here. So these two probabilities will cancel out, and what I get is simply the sum. Now this measurement was performed on B, and I am not looking at the outcome because this is what this summation over B here is achieving. So even though the global state has changed because I've performed a measurement, I've performed an operation, of course it has changed, the reduced density on A has not changed. This operation was local to the B system. So if my goal is to compute a description of the A system, I can try to compute it from Rho AB, and that's kind of complicated because I don't know what Rho AB is, or I can compute it from the state Rho tilde AB. I should get the same outcome. But now Rho tilde AB has the advantage that it's a state of the same form as the one we considered earlier. It's simply a mixture of tensor product states. And in that case, it's pretty clear what the reduced density on A should be. It should be the same mixture, where in each component I just consider the tensor factor that's associated to the A system. So I would just get the sum over B of these expressions here, identity tensored projection on B, Rho AB, identity tensored B. And now this gives me a formula for my reduced density. It must be equal to this expression, whatever measurement I choose to perform on the system B. So this is a formula for taking the partial trace. Let's look at it a little bit more. So I just copied for you here the formula that we obtained on the previous slide, and this was obtained by choosing any basis B for system B. Now we have a candidate definition. Let's see that it makes sense. So let's do a few sanity checks and play around with this. One thing of a new definition that we always want is that it works in simple cases. So there's cases where we know what the answer should be. For instance, if the density matrix Rho AB is a tensor product of two density matrices, Rho A and Rho B, then for sure I want my reduced density on A to be equal to Rho A. Is this the case with the definition that I've given you? Let's check. So let's compute the sum over B of identity tensored B applied to Rho A tensored Rho B, so assuming that I start off with this tensor product. So now each of the term is the product of three tensor products, so I can use distributivity, and it's going to simplify to sum over B of Rho A tensored B, Rho B, B. And now using that I'm summing over the elements of a basis, what I recognize here is Rho A tensored the sum over B of the overlap of Rho B on B, and that's simply the trace of Rho B. And now because Rho B is a density matrix, its trace is 1, and I simply recover Rho A as desired. So the first sanity check passes. Good. Let's do a second sanity check. I am calling this a reduced density matrix. I am calling it a mixed state, a description of the state on system A. We should make sure that this thing is always indeed a density matrix. So we should verify that it's positive semi-definite and has trace 1. One thing that's clear from the definition is that it's Hermitian. So in order to check that it's positive semi-definite, I only need to verify that its overlap with any pure state is positive. So let's check that. Let's take a pure state phi, compute the overlap phi on Rho A. I can use linearity to rewrite this as the sum over B of the overlap of the tensor product of phi and B with the state Rho AB. And now Rho AB is our starting point, it's a density matrix, so each of these overlaps should be non-negative. I'm summing over non-negative terms, I get an expression that's non-negative. So this passes. The other thing that we want to do is compute the trace. So let's compute the trace of Rho A. For this we can choose any basis of the A system and sum over that basis. So now we have a basis for A, a basis for B, and we compute the overlaps. We have a basis A for the system A, a basis B for the system B, and I consider all possible tensor products, A tensor B. This is a basis for the joint system A and B. So what I'm doing here is really just computing the trace of Rho AB, which, since Rho AB is a valid density matrix, is equal to 1. So I verified that my matrix Rho A is positive and has trace 1. It's a valid density matrix. This sanity check passes. Excellent. Now there's one last sanity check that maybe we should have performed first, which is that I'm giving you a definition, but the way I gave you the definition was to start off by saying choose any basis of the B system and then do this and that. Who guarantees me that the object that I get in the end is independent of the choice of basis that I made in order to compute the object? If really I can call it Rho A, it should not depend on this basis, and this is something that we should absolutely verify, so let's do it. So I copied again the definition for you. Now I know that Rho A is a density matrix. Let's compute its overlap with any pure state phi. This is a calculation that we already started before. I can rewrite this as the sum over B of overlap of the tensor product of phi and B with my state Rho AB. And now let's use linearity and cyclicity of the trace to rewrite this as follows. The trace of an expression which is the rank 1 projection on phi tensored with the sum over B of the rank 1 projections on B, the whole thing multiplied by Rho AB. How did I get here? I used two things. The first is cyclicity, which lets you move this bra phi over there and this bra B over there. And the second is linearity of the trace, which lets you take the summation outside. And if you use these two properties, you can see that the second expression that I wrote is equal to the one on the first line. What's good about this now is that I'm summing over all B of the rank 1 projections on B, and B is a basis, so this expression here is simply equal to the identity matrix. And so I can rewrite the expression that I obtained as follows: the trace of rank 1 projection on phi, tensored identity, multiplied by Rho AB. And you see that the end result here, no more mention of the basis B, it's been replaced by the identity. So this last expression is independent of the choice of basis that I made, which means that the initial expression, the overlap of Rho A as I defined it with any pure state phi, is independent of the choice of basis that's made in the computation of Rho A, which means that Rho A itself is independent of the choice of the basis B. Good. Our third sanity check passes. One last thing that I want to point out though is that this freedom in the choice of basis B is something that's going to be very useful in calculations. In general, you'll be given a state Rho AB in a certain form, might be a mixed state or might be a pure state, and that form is often going to give you an idea of what basis you should choose to make the measurement on system B that's going to make the calculations easier. Of course, this measurement is not something that you perform at any point. It's just something that's used to do the calculation. In this expression, even though the result when you sum over all B is independent of the choice of the basis B, when you actually have to compute it, it's important to make a choice of basis B that makes the computation easier. And we see an example of how to make the right choice of basis in the next example module.